Hello everyone, welcome back to my channel, and in today's video we are going to solve two problems from recent test series. So first question states that we have a uniformly charged spherical shell B whose charge is Q. It is kept inside a uniformly charged hemispherical shell A with the same charge Q. Let electric fields due to A and B at any points be EA and EB vector. If dV represents the elementary volume, then the value of this integral will be. Now if dV represents elementary volume, then the value of this particular integral will be. So the numerator, if you simplify it, is just the space integral. Space integral just means that we integrate from r equals 0 to r equals infinity, covering the whole space basically. The space integral of EB dot EB. EB dot EB. Now, if you dot a vector with itself, you'll just get the modulus of that vector squared. So this is simply going to be EB squared and this dV. Okay, so this integral is pretty familiar because let's say if I separately draw our sphere B, which has a uniform charge density of plus Q on its surface. If I want to figure out the energy stored in the electric field of this spherical shell, then one way I can determine it is by using the idea of energy density, right? So the electrical energy density, which I'm going to represent by small u, is half epsilon naught E squared. And this is also the energy stored per unit volume, right? So if I want the energy stored in just B's electric field, so forget about the shell A for a moment, guys. Then what I will do is, I know the energy per unit volume, so I'll just do a volume integral of the energy density. So this just comes out to be half epsilon naught integral of E squared dV, right? And this just turns out to be the self energy of the shell B, which was actually kq square by 2r. So if I assume the charge on the shell B is B and its radius is r, its self energy we know it is kq square by 2r, and which is also equal to this particular integral over here. So basically the space integral of EB square dV is nothing but kq squared divided by epsilon naught r. So what I did is I send the epsilon naught to the denominator. So the numerator simplifies as this particular value. It's related to the self energy of the shell B. And now if you observe in the denominator, now they're asking the integral of EA dot EB. So for this we have to discuss one more concept. Okay, for this obviously we are not going to do EA dot EB, right? So because that is going to get very complicated. It'll depend, it'll vary from position to position. Okay guys, so for the sake of an example, I am taking two charged spheres, let's say one with charge Q1 and another sphere of charge Q2. Okay, and now let's say I want to figure out the total energy stored in the electric field of this system. Now if you said the answer to this question is half epsilon naught E1 square dV plus half epsilon naught E2 square dV, this is actually wrong, and the reason for that is the energy doesn't add linearly. So the total energy is not going to be E1 plus E2. We can do something else. So if let's say I take a small elementary volume of dV somewhere, and let's say the electric field due to sphere 1 is E1 over here, and the electric field due to sphere Q2 is E2 at that location, then the energy density at that location becomes epsilon naught, the net electric field at that location, which is E1 vector plus E2 vector, the modulus of that squared. So we know that electric fields add vectorially, so we can figure out the energy density. So now the thing is, for the total energy, we are going to perform the space integral of U. Mod of E1 plus mod of E2 squared will be E1 squared plus E2 squared plus 2 E1 dot E2. So I'm going to take the half epsilon naught outside. So this will just be E1 square dV plus integral of E2 square dV plus twice of E1 dot E2 dV. So the integral will consist of these three particular terms over here. Now if you observe something, this half epsilon naught E1 square is just the self energy of sphere 1 as we discussed in the last page, right? So I'm going to write it as U self due to sphere 1, and similarly half epsilon naught E2 square will correspond to the self energy of sphere 2. And then we have an additional term which is epsilon naught, the 2's cancel out, E1 vector dot E2 vector times dV, and this is kind of what they asked in the denominator, right? But the thing is, how do we figure this out? Okay, so that's the tough part, and this is something that you guys have to take my word for. Like, I'm not going to be proving this. We are going to discuss a slightly different problem. So let's say if I take two point charges Q1 and Q2, which are separated by a distance of L. And if I ask you what is the interaction energy of this charge Q1 with the other charge Q2, you would say it's simply K Q1 Q2 divided by the separation between them, which is L. If you guys perform this particular integral, which is basically epsilon naught integral of E1 vector dot E2 vector dv, and if you perform the space integral of this, then what you get is k q1 q2 divided by L. And you can actually prove this. It'll take some math. It'll like make the video like 10-20 minutes longer if I went to prove this. It'll take spherical coordinates and some slightly complicated integration to prove this. So that's why I'm saying, like, just take my word for it. The answer to this is the same as the interaction energy. So basically what I'm asserting is this term over here represents the interaction energy, the energy due to the interaction between different charges. Okay, and these terms, as you can see, tell us about the self energies. Okay, so basically what the denominator is hinting at is what is the interaction energy between sphere A and sphere B. I mean, not exactly, because there should be an epsilon naught as well, but that we'll modify. So that is what we are going to figure out next. Okay guys, so in our problem, sphere A has a charge Q and radius 4r, and sphere B also has a charge of Q and it has a radius of capital R. Okay, so the thing is, as we discussed in the previous page, the integral of epsilon naught E1 vector dot E2 vector dv, this represents the interaction energy. This represents the interaction energy. So ultimately all we have to do is figure out what is the interaction energy between sphere A and sphere B. And that is pretty easy to write in this case, because we know due to sphere A, potential everywhere inside is a constant, right? Forget about the shell B for a second and just focus on A. So we know that it is a uniformly charged sphere, and which basically means everywhere inside the potential is a constant, and it is equal to K times the charge divided by the radius of the sphere, right? And it is the same for all points inside. So, and now let's say if you take a small dq charge somewhere on the surface of sphere B. So the interaction energy of this dq charge with the outer sphere, let's call it du, it is equal to the potential at the location of dq multiplied by the charge dq. Okay, so this is the interaction energy of the small charge dq with the entire sphere A. So if you integrate it for all such charges dq lying on the surface of sphere B, then you'll get the total interaction energy. And that just comes out, and v is a constant here, so you can take it out of the integral, and integral of dq will give you the charge of sphere B, which is just q. So v is nothing but kq by 4r, so this just becomes kq square divided by 4r. So we finally figured out the value of this integral. It is kq square by 4r. Now the denominator in our current problem was integral of E1 dot E2 times dv, so this would just become kq square divided by 4r epsilon naught. Okay, so the answer will be kq square divided by r epsilon naught divided by kq square divided by 4r epsilon naught, and this will just give you the answer as 4. So now let's move on to the next question. So okay guys, so in this question we have a cylindrical massless cork whose length is L and radius is given to be small r. It is slowly extracted from the neck of a bottom opened bottle. If the normal pressure between the bottle and the unextracted part of the cork at any instant is constant and is equal to P, the work done in extracting it completely is. So the mu between the bottle and the cork is given. So basically what they're saying is, let's say we pull it out by a little bit. So then the pressure that the bottle applies on the cork throughout its curved surface area is constant. So we have to figure out the work which we have to perform to pull this out completely. Okay guys, so let's say this is the cork, okay, and this white line represents the initial position of the cork. Okay, so now let's say we pulled it out of the bottle by some distance of x. So at this particular moment, only L minus x length of the cork is present inside the bottle, which means the pressure or the normal force is only acting on this part of the cork, and also friction is also the same. So the friction forces will only act on the cork on the parts which are inside the bottle. Okay, so now let's say this is a side view of the situation and we are pulling it out in this direction. Okay, so now let's say we take a small patch of area dA on the surface of our cylinder. Now obviously this area is going to slip with the inner surface of the bottle, and as it is slipping towards the left, a force of friction will act in the backward direction. So let's say that force of friction is dF. Okay, so and the normal force acting on this patch, we can figure it out pretty easily. We know that the normal force that the bottle applies on the cork per unit area is equal to the pressure P. So we can figure, so from here the normal force just comes out to be P multiplied by dA. Okay, so now as the friction is kinetic in nature, I can say that the friction force is mu times dN, which is mu times P times dA. And obviously its direction is opposite to the direction of the applied force, right? Now guys, for all such dA elements on the cylinder, the force of friction is same, right? It is acting opposite to the direction of the applied force. So therefore, as the direction is the same, we can obtain the total friction force by just integrating dF. So this is equal to mu, P is a constant, so we can take it out, times integral of dA. Integral dA is the area on which friction force is acting. So that corresponds to the lateral surface area of this part, which I'm marking with yellow. And this has a length of L minus X and a circumference of 2 pi r. So integral dA will become mu P times 2 pi r into L minus X. Okay. All right. So now we have friction force, and obviously, as you can see, it comes out as a function of X. So now let's say we pull this cork out by a small distance of dx. Okay. And for that, let's say the small work that our agent has to do is dW, and obviously the only force that we have to work against is friction force. So this will be equal to the friction force F dot dx. And in order to get the total work done, all we have to do is integrate this. Okay, and the limits of X is obviously from 0, which represents the initial situation, and finally a complete L length is out, so the value of X will be L. And once you integrate the expression, you'll get the answer as 9 joules. Okay, so that was it for this video, guys. So I'll come up with more videos soon. So if you enjoyed the video, please do like, share and subscribe. And that's it. Thanks for watching.